So we're starting on chapter 4, section 4.1, and we're dealing with cubic graphs. And once we've dealt with cubic graphs, we'll also be able to deal with quartics sort of straight away. So first of all, let's just get the idea. Cubic graphs, we're looking at things that look like this. Something times x cubed plus something times x squared plus something times x plus something. So it's a quadratic with a cubic term in x stuck on the front of it, okay? Now, we already know from GCSE kind of roughly what these look like, but let's just think of it as though we don't know for the start, to start with rather. Now, what we do know is this. If I had three brackets with an x term and a constant term in them, so something times x plus something, something times x plus something else times x times something else, that would expand out to a cubic, wouldn't it? So if I had one of these, it would look like that. And if I was looking at this function, sorry, those aren't threes, they're just, you know, this is some number, right? So if I had this thing and I was looking for the roots of this function, that would be the solutions to 0 equals these three brackets. So each one of those brackets would give me one root, wouldn't it? Okay, three things times together to make 0. One of those things must be 0. So either this is 0, or this is 0. So there would be three roots. So in other words, this cubic that can be factorised would have three x-axis crossing points, okay? Because the related equation has three solutions, i.e. the function has three roots. If those words don't make sense, then go back and have a look at chapter 3 stuff. So that's the first observation. We get three x-axis crossing points. Okay, now that would give us, if we just put three crosses anywhere, in fact, let's not bother with the y-axis even, let's just have a horizontal line with three crosses on it, okay? I'm going to cross the axis somewhere. Well, if I'm going to cross the axis here and here again, I've got to turn round. So there's got to be a turning point here, and I've got to go from the axis back to the axis. And then I'm going to hit the axis here, I'm going to have to turn around again. And that gives us this sort of shape, doesn't it? So just from the idea that I can have three x-axis crossing points, if I've got a function that has three x-axis crossing points, it's got to look roughly like this. I can't turn round again. This has got to keep going, because if it turns around again, then even if it sort of turned here just for a little bit and then turns around, well, I could slide the function up and down so the x-axis was this line here, and then there would be more than three crossing points. So if I've got three crossing points and only three crossing points, oops, then I must have this sort of a shape, okay? It must zoom off to infinity here and not turn around, zoom down to infinity here and not turn around, and then have sort of two turning points in the middle. So some cubics look like that. So some cubics can be factorised into three brackets, and when they can be factorised into three brackets, there will be three solutions to this equation, and if there are three solutions to this equation, there's three roots, that means three x-axis crossing points, and that's where the shape comes from, okay? Now, we know as well from GCSE that if the a, the coefficient of x cubed, is positive, then I get this shape, and if it's negative, I get this shape. So a is bigger than 0, a is less than 0. Well, we can see that by thinking like this. If I take, let's say this is my y-axis, this is my x-axis, y-axis, x-axis. Now, if I take a very, very positive number, right? So if I go a long, long way to the right along my x-axis, then what's going to happen? Well, if I get a very big number, x cubed is bigger than x, and x squared is bigger than x, and x cubed is bigger than x squared. Even if these coefficients here are big numbers, right? So let's say b was 1,000,000. Well, just keep going along the x-axis until x cubed is 10 times bigger than that. If you know, x cubed can be 1,000,000,000,000, and then whatever this b is starts to look small, okay? So it doesn't matter what the constants are. Eventually, the x cubed term is going to be a lot bigger than the x squared term, and a lot bigger than the x term, and a lot bigger than the constant term. And if you're not at the point on the x-axis where that's true yet, then just keep going until you get to a really big number for x. That'll be a really, really, really big number for x cubed, and we're away, okay? So if we go far enough along the x-axis, this whole cubic function is going to look like x cubed times a. Okay, and x cubed times a, well, if x is a really, really big positive number, x cubed is a really big positive number. If a is positive, then I get a value somewhere up here in the positive y-axis, and it's just going to keep getting bigger. Same argument, if a is positive and x is a really, really big negative number, then we're down here. Okay, so the graph has to come from negative infinity. Eventually it goes off to positive infinity, and it can only cross the x-axis a maximum of 3 times in between. So that's where we get that shape. That's where a is positive gives us this one. And if you just repeat the same sort of argument with a being negative, if x is a negative number, x cubed is negative. If a is negative, then when you times it by a, that gives you a positive. And well, feel free to fast forward, but let me say it for those people that want to hear it. If x is a very, very big positive number, x cubed is a very, very big positive number. If a is negative, we've got a positive times a negative, so I get a very, very big negative number. And that's where our shape comes from a is less than 0. Now then, we've established then that the cubic can be something sort of this kind of shape, and that's totally true. But we know from quadratics that you can't always factorise a quadratic into 2 brackets. And same with cubics, you can't always factorise it into 3 neat brackets. So we have a few exceptions to this, and what we get is the following situations. We can sometimes have this, where we get we get one x-axis crossing point and one x-axis meeting point. So this is a root, this is a repeated root. In the cubic expression for this function, that would look something like this. We'd get one bracket, and then we get another bracket with a squared on it. So this might be x minus 2 squared. This might be x plus 3. Okay? So x minus 2 would lead to the solution x equals 2, and it's squared. So at x equals 2, we would get a meeting point between the graph and the x-axis. The turning point of the graph just touches the x-axis. X plus 3 would lead to a solution of the equation 0 equals x plus 3, just to be picky about the difference between functions and equations. If I've got an x plus 3 in the function in brackets, then this equation has a solution at x equals minus 3, and it's just a straightforward, there's no squared on it, so we just cut through the axis. So that's one of the possibilities we can have. Another possibility would be, and we've seen this before with cubics, I know, where we have a point of inflection. And the way to think about that is if you have a cubic graph with 2 distinct turning points, and then those turning points kind of get closer and closer together, then eventually you end up with the gradient goes positive, 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 very, very small, but still positive, still positive, still positive, and it gets closer and closer to 0. And then there's one x value, where if we drew the tangent onto this graph, we'd get a horizontal tangent, right? There'd be one x value where the gradient is strictly speaking 0, and then the gradient takes off again and is positive after that, okay? Contrast that with a turning point where the gradient is positive, gets smaller. There's one point where the tangent is horizontal, so the gradient of the tangent is 0, so the gradient of the curve is 0 for one x value, and then after that point the gradient is negative, 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 and getting more negative, okay? So this point here we're going to call a point of inflection, and it happens when these two crossing points we adjust the coefficients of the x cubed, x squared, and so on in such a way that these points kind of get closer together and eventually merge into just a sort of flattening out of the curve, and then it takes off again. So I can have a cubic which looks like this. I can have a cubic which looks like this. So this one has a point of inflection and only has one x-axis crossing point. This one has no point of inflection, but all the interesting stuff happens up here away from the x-axis, so we only have one x-axis crossing point. Or I could have a cubic that looks like this. I'm being a bit sloppy about my x's and y's on my axes, well, hopefully you'll forgive me for that, where the point of inflection actually lies on the x-axis, and that is going to look like y equals x plus something or other cubed. So if you end up with a cubic of this form, you've got three roots meeting together on the x-axis, and that's where the point of inflection is going to hit the x-axis there. So I think we've kind of covered everything we need to there with the cubics. We need to know about repeated roots. We need to know that we can, if we factorize it, we can see where it hits the x-axis. Remember from chapter 3, the trick of it hits the y-axis when you put x equal to 0 in the equation and work out what y is. It hits the x-axis when you put y equal to 0 in the equation and work out what x is, and so on. If you're not happy with the language of functions and roots and equations and solutions to equations being roots of the function and that sort of thing, please do go back and look at chapter 3. It's really important to get those ideas straight. There is a video on this channel about that. Okay, so we dealt with cubics. Well, what happens with quartics? Well, with quartics, we've got an x to the power of 4 at the front of a cubic. So ax to the power of 4, bx cubed plus cx squared plus dx plus e. And if we put that equal to y, well, again, let's just use the same logic. If I had 4 brackets, each with an x and a something else, x and a constant term in, so something times x plus something, something times x plus something else, something times x plus something else, something times x plus something else. If I times those 4 brackets together, I get a quartic. Therefore, this function, if we look at this equation, if we put that equal to 0, we would get 4 solutions. So there would be 4 roots to that function. If that function has got 4 roots, there are 4 x-axis crossing points. They might be close together, they might be spaced out. But if we got 4 x-axis crossing points, then it could look like this, or it could look like this. 1, 2, 3, 4. Okay? And hopefully you're starting to see a pattern. A quadratic, where we have the biggest power on the x is x squared, looks like this. A cubic is this sort of shape. A quartic, so what do these look like? 1 turning point for x squared, 2 turning points for x cubed, 3 turning points for x to the power of 4, and x to the power of 5, a quintic, would have 1, 2, 3, 4, 1, 2, 3, 4 turning points. Okay? Now, again, the same thing applies to quartics as did to quadratics and to cubics, which is that we might have repeated roots. So this might be not 4 brackets, but 3 brackets and a squared on one of them, or not 4 brackets, but something cubed and a bracket on its own. So what you've got to remember is if there is a higher power on the bracket, then there is something interesting going on. If there's a squared on the bracket, then you get a turning point hitting the axis. Okay. So what do we need to know? We need to get this sort of idea. We've got a function here with 4 distinct linear factors. If we take those, that will give us 4 distinct x-axis crossing points, 4 roots, and we get this sort of shape quartic. If we've got this one here, where we've got an x, that's 1 linear factor, x plus 2 squared, so that's a repeated root, and 3 minus x. So we get 2 crossing points from the x and the 3 minus x, and this one is the repeated root because there's a squared on it, so there's a turning point that touches the axis. Okay. We do get quartics where all of these 3 turning points melt together as they did with the cubics, and what we get there isn't a point of inflection. It's still a turning point, but it's a turning point with a sort of flatter turning pot, you know. So either the bottom bit, or if it's an upside down one, the top bit are sort of flattened out a little bit. So it looks, if you made a quick sketch, it might look a bit like a quadratic, but if you were to sketch them on your calculator or on some sketching graph software, you'd see a different sort of shape. So there we go, quartics and cubics. Oh, and the only thing we haven't said, of course, is when do we get the this sort of shape quartic with the arms going down here and down here, and when do we get this one which starts at the top and ends up at the top? And again, just think about it. The x to the power of 4 term, if you go far enough along the x-axis to the right or to the left, the x to the power of 4 term is going to take over from the other ones. So it's just a case of looking at the power on it. So if x is very, very big and positive, x to the power of 4 is very, very big and positive. If a is positive, then it's going to be up there. If a is positive, x to the power of 4 is very, very big and positive, so a is going to be positive as well. So a being bigger than 0 is one of these shape ones. Whoops, there we go. A being less than 0 is that sort of shape one, because if x is very, very big, either positive or negative, x to the power of 4 is always positive. If a is less than 0, a times x to the power of 4 will be negative and negative. Okay, that is all the information on section 4.2 and 4.1.